a proper closed linear subspace. Therefore, if M is proper, there exists at least one Z naught in H which is not in M. Therefore, by using this fact, we have proved that this Z naught is orthogonal to M. This is the first theorem we have seen. In the second theorem, we have seen the if and only if statement for a linear subspace M of a Hilbert space H, that M is closed if and only if M is equal to M double perp. Okay, what this perp is? Orthogonal complement. M double perp will be twice the orthogonal complement of the set M. Therefore, the set M is closed if and only if M is equal to M double perp. Okay, and then third theorem we have seen is if M and N are closed linear subspaces of a Hilbert space H such that M is orthogonal to N, then the linear subspace M plus N is closed. Okay, what is the condition? Both should be closed linear subspaces and they should be orthogonal to one another. Then M plus N is closed. This is the third theorem. And fourth one, we have seen the orthogonal decomposition theorem. In the orthogonal decomposition, we have factorized the given Hilbert space into two parts. Which two parts? If M is a closed linear subspace, okay, if M is closed linear subspace, it will be one part of the factorization, and its orthogonal complement M perp will be the other part of the factorization. In this way, H is being divided into two parts, M and M perp. We are writing it is a direct sum. The meaning of direct sum is there is a intersection of both the sets M and M perp will be singleton 0, right? Intersection of M and M perp will be singleton 0. This is orthogonal decomposition theorem, which is actually the factorization of the given Hilbert spaces. Okay, now let us move ahead today. The first theorem we are going to understand is, okay, see, I'll write the theorem first. This is number 14. As I told you in the last lecture, I have given a numbering to the theorems so that to recall the theorem will be easier for us. Okay, now this is the number 14 theorem. Statement is, let S be non-empty subset. Let S be a non-empty subset of Hilbert space H, then the set of all linear combinations of vectors in S is dense in H, if and only if S perp is equal to singleton 0, or we can write let S be non-empty subset of Hilbert space, non-empty subset of a Hilbert space, then prove that generated by S, this is set of all linear combinations generated by S, is dense in H if and only S perp is equal to singleton 0. If and only S perp is equals to singleton 0. Let me make full screen. Okay. Therefore, the theorem we want to prove is in two parts. Okay. If and only if statement is given to us. What statement says that for any non-empty subset of a Hilbert space generated by S is dense in H. What do we mean by dense in H? If any subset we want to prove dense in any other subset, that is suppose A we want to prove dense in R, then what we are writing? A bar closure of A is equal to R. Na? Likewise, here also we will do the same thing, dense in H. This is if and only if S per, that is orthogonal complement of the given set is singleton 0. Okay, let us prove the result in two parts. Part 1 we will consider, we will first assume that this generated by S is dense in H. Okay, and our aim will be to prove S perp is equal to singleton 0. Okay, I'll write, let generated by S the set of denote the set of all linear combinations, set of all linear combinations of vectors in S. For the sake of convenience, we will call the set to be M. M is generated by S. Now what is my assumption? Generated by S is dense in H. Therefore that is, one can write, let us assume M is dense in H. Let us assume M is dense in H. Okay, if M is dense in H, what does this implies? M bar is equal to H, set of all closure. Closure of M is equal to H. And what is the aim to prove? S perp is equal to singleton 0. Okay, what actually we want to prove is, that is whenever X is orthogonal to S, X is in S perp means X is orthogonal to S, implies that X is equal to 0. This is what actually the aim is. Okay, in order to prove this result, first we will try to prove that any element which is orthogonal to M will be orthogonal to M bar also. Okay, therefore here I will write, first we show that wait for a moment. First first we show that X is orthogonal to M implies X is orthogonal to M bar. Okay, because this statement is going to help us to prove the given result. In order to prove X is orthogonal to M bar, what actually it means? Okay, that is to prove that whenever X is orthogonal to, that is X is orthogonal to Y for all Y in M bar. Right now, we want to prove the vector X orthogonal to the set M bar. It means clearly that X is orthogonal to every vector Y in M bar. Okay, now let us start with a vector Y in M bar, and we will prove that this inner product is 0. Correct? Therefore, let us start with Y in M bar. If Y is an element in M bar, what does it mean? Y is limit point of the set M. Correct, no? It is in the closure. Y is a limit point of the set M. If Y is a limit point, what does it implies again? There exists a sequence Yn in M such that, what such that? Yn tends to Y as n tends to infinity. Let me call this as statement number 1. Okay, there exists a sequence yn in M such that yn tends to or converges to Y as n tends to infinity. Now, yn we have selected from M now. Yn is an element of M. Okay, but what is the assumption we have made? X orthogonal to M implies X is orthogonal to M bar. Therefore, let me assume, or here one can write, let Y is belonging to M bar, X is orthogonal to M. Therefore, if X is orthogonal to M, Yn is an element of M. Therefore, may I say X is orthogonal to Yn also? Correct, na? See, this is the situation I am saying. Okay, if this is M bar, Yn is an element in M bar. Oh, sorry, this is M I'll call. If this is M, Yn is an element of M, and X we are saying orthogonal to M. X is orthogonal to M. Therefore, X must be orthogonal to Yn. If X is orthogonal to Yn, inner product X with Yn is equal to 0, and this is true for all N. Let me call this as statement number 2. Right? But in one of the theorems, we have seen that inner product is a continuous function, as inner product is continuous function. as inner product is continuous function. What does this mean? Inner product x with yn will converge to inner product x with y as n tends to infinity. From this statement we are writing yn converges to y implies inner product x with yn converges to inner product x with y. Again we will call this to be statement number 3. Again, we will call this to be statement number 3. Now, look at statement number 2 and 3 carefully. Statement number 2 is saying that every element in this sequence is 0. Inner product x with yn is 0. Therefore, what should be a limit point? Sequence of all zeros must converge to 0 itself. Okay. Therefore, from 2 and 3, may I say inner product x with y is equal to 0. Inner product x with y is equal to 0 for all y in m bar. We have initially started with y in m bar itself. Correct? Na? Y in m bar. Therefore, what we have proved? That x is orthogonal. X is orthogonal to y for all y in m bar. Thus x orthogonal to m implies x is orthogonal to m bar. This we have proved. Okay. Now we want to prove we will use the statement for proving the actual result. Okay. What is my actual result to prove? S perp is equal to singleton 0. Now what the job we will do? We will start with one element, say x in S perp, and we will show that x is equal to 0. Right? Therefore, let us start with, let x be an element in S perp. Okay. The aim is to show that x is equal to 0. Let me call it as statement number 4. If x is belonging to S perp, what does it mean? X is orthogonal to S. Right now, x is orthogonal to it. But what m we have defined? M we have defined the set generated by S. Now, if x is orthogonal to S, may I say x is orthogonal to m also? Okay, try to get me. S is always contained in generated by S. S is always contained in m. Okay, that is S is contained in m. Therefore, if x is orthogonal to S, m is the set of all linear combinations of elements of x. Therefore, x is also orthogonal to the elements. Okay. Therefore, here I'll write, since m is set of all finite linear combinations of S, this implies, or therefore x orthogonal to S implies, x orthogonal to S implies x is orthogonal to m. But just now we have proved x orthogonal to m implies x orthogonal to m bar. Okay, here is the statement we have proved, right? Therefore, x orthogonal to m bar. But what is m bar? M bar is H. Correct na? This is the call it as some star. M is dense in H, na? Therefore, m bar is equals to, by star I will write, by star. Therefore, x is orthogonal to H. Now we have started with x to be an element. We have started with x to be an element in S perp. S perp is no doubt an element in H. And now we are saying x is orthogonal to H. Therefore, S perp is contained in H. Therefore, x is an element of H also. Now we are saying x is orthogonal to all. Therefore, I will say that x is orthogonal to x, because x is again a member of H. Right? But when this situation is possible, x is orthogonal to x, this is possible only if x is equal to 0. This is possible only if x is equal to is equal to 0. Therefore, here we have started with x is in S perp and we have proved S is equal to 0. Therefore, may I say the elements in S perp is only 0. Therefore, S perp is singleton 0. Or one can say, if someone wants to write like this also, one can write S perp is contained in singleton 0, because x is in S perp implies x is equal to 0. But as S perp is a subspace, singleton 0 is always contained in S perp. Combining both the results, one can say S perp is equal to singleton 0. Hence, it is the proof of first part of the statement. Now, let us go to the second part. In part 2, what should be the assumption? The assumption should be S perp is singleton 0. Let us assume S perp is equal to singleton 0. What to prove? What to prove? Generated by S is dense in H. Generated by S is dense in H. That is M bar is equal to H. Na? M is equal to generated by S. We have defined already. Symbol we have written simply. Okay. Our aim is to prove M bar is equal to H. So this is the situation. M is the subspace of H. Okay, and our aim is to prove that the set of all closure M is equal to H. To prove this, let us assume the contradiction that M bar is not equal to H. What is the only possibility? M bar will be proper subspace of H. Okay, let us assume the contradiction. Let us assume the contradiction. Now, what is the contradiction? M bar is not equal to H. That is, M bar will be theorem. What is the theorem? Okay, before that, M bar, that is, I'll write M bar is proper subspace of H. If it is proper subspace, may I say there exists an element X in H but not in M bar. Not in M bar. Okay, let me call this to be statement number next, say 5. Okay, now as M bar is a proper subspace of H, now we will use the, here I will make M bar. Okay, if M bar is proper subspace of, now we will use orthogonal decomposition theorem. What orthogonal decomposition theorem says? Whenever we have a proper subspace of a Hilbert space, then H can be factorized into two parts. One is M bar, other is M bar, its orthogonal complement, right? Therefore, I will write by orthogonal complement, orthogonal decomposition theorem. I'll write full. Orthogonal decomposition theorem by orthogonal decomposition theorem. Why orthogonal decomposition I can use? Because M bar is closed always, right? Na? M bar is closed subspace, closed proper subspace of H. Therefore, H I can write as M bar direct sum M bar complement M bar perp. Okay. Now, any element X in H, okay, any element X in H, where H is M bar direct sum M bar complement, can be written as, how can I write X as Y plus Z, where Y is in M bar and Z is in M bar complement, M bar perp. Correct now? But here, whatever is Z we are writing as an element of M bar complement, this Z cannot be a zero vector. Here, Z cannot be 0. What will happen if Z is 0? Z cannot be 0 because, let us check what will happen. Because if Z is equal to 0, what is X? X is equal to Y plus 0 is equal to Y. Right now, therefore this Y will be a member of M bar. Y will be a member of M bar. Okay, that is x is in m bar, that is x is in m bar and y is in m bar. Here we have not taken any element of m bar perp. Correct now? Whenever we are writing h to be a direct sum of m plus m bar perp, what should be a unique representation? I'll just write here. Okay. Whenever we are writing a set x to be a direct sum of two subsets, then any vector x in x is uniquely written as x is equal to a plus b, where a is in a and b is in b. This should be a situation. Every element is uniquely written as one element in one set added with one element in another set, and this should be a unique representation. But what here we have obtained? X is an element of m bar we have obtained, but this should not be true. This we have obtained because of the assumption z is equal to 0. Hence z cannot be a zero vector. Hence z is a non-zero vector. Hence z non-zero. Hence z is zero. Thus there is a non-zero vector. There is a non-zero vector z in m bar perp. Correct na? Where is z? Z is in m bar perp. Okay? Non-zero. Okay, be sure that z is non-zero. Therefore, z is in m bar perp. Okay, z is in m bar perp implies z is orthogonal to m bar. Z is orthogonal to m bar, and since m is subset of m bar, it implies z is orthogonal to m also. Right now, z is orthogonal to a bigger set. Therefore, z must be orthogonal to m. Okay, now z orthogonal to m bar, m is contained in m bar, implies z is orthogonal to m. This implies z is member of m bar perp. Let me call this as 6, I think. I'll just check the number. Yes, it is 6. Therefore, z is in m bar. Okay, we have started with z is in m bar perp. We obtained z is in m perp. Okay, but as s contained in m implies m perp is contained in s perp. Reason, consequence number 4. Consequence number 4. Okay, now here we are writing z is in m perp. It implies z is in s perp. Z is in s perp. Correct now? Okay. Z is in m from 6, and I'll call this as 7. The further reason I will write is from 6 and 7. Okay, what we have seen from 6 and 7. Okay, we'll just recall. There is part 2 we have started. We have started with S perp is singleton 0. To prove that it is dense in H, that is to prove M bar is in H, we have made the contradictory assumption that M bar is proper subspace of H. If it is proper, there exists X in H but not in M bar. Okay, for this, let us use the orthogonal decomposition theorem. H is divided into two parts, M bar direct sum, M bar perp. Therefore, every x in H is written as the addition of two different elements, y and z. Y is in m bar, z is in m bar perp. Here z cannot be 0 because if z is 0, this x will be the element of m bar only. Therefore, here we have we have obtained that z is a non-zero vector in m bar perp. Z is an m bar perp implies z is orthogonal to m bar. Since m is contained in m bar, it gives us z is orthogonal to m also. Therefore, z is belonging to m perp. As S is contained in M perp is contained in S perp. Therefore, Z will go in S perp. Now we have found a non-zero vector Z in S perp, which is a contradiction to the assumption. To the assumption S perp is singleton 0. Therefore, this is a contradiction. This is a Contradiction to the assumption. Contradiction to the assumption. What is the assumption we have made? Contradiction to the assumption S perp is equal to singleton 0. There is only 0 vector in S perp, but we have found a non-zero vector Z in S perp, which is the contradiction. Contradiction arises due to a wrong assumption that M bar is proper subspace of H. Hence, I can write M bar is equal to H. Thus M equal to generated by S is dense in H. Is dense in H. Yes? Any doubt with the proof? Yes, students?
No,
Any
ma'am.
doubt up to this?
No, ma'am.
No, ma'am.
Acha, good. Now we will go to the next theorem. Acha, before a theorem, there is a new concept called as orthonormal sets. Okay, we will just deal with the next concept. Heading is orthonormal sets. Normal set. Okay, before going to understand orthonormal set, we need to know a definition of a unit vector. Can anybody tell me what is a unit vector? Yes, from students, can anybody tell me a unit vector?
The norm of a vector is equal to 1, then it's said to be a unit vector.
Yes, the norm value is 1. Okay, therefore if H, let H be Hilbert space, okay, X is in H, such that norm X is equal to 1, then X is said to be unit vector. Norm X means what? It's a distance, the distance of the vector X from the origin. Then X is said to be unit vector. Okay, now in the definition of an orthonormal set, we are going to collect all unit vectors. Okay, see what I'm saying? In the orthonormal set, we are collecting all the unit vectors which are mutually orthogonal to one another. Which are mutually orthogonal to one another. For example, in a three-dimensional space, we have the coordinate axis, na? See like this. X-axis, y-axis and z-axis. All the three axes are mutually orthogonal. Correct na? X is orthogonal to the remaining two. Y is orthogonal to the x and z. Likewise, means all the three vectors, all the three axes are mutually orthogonal. Therefore, if we consider the unit vectors on every axis, what will happen? What will happen? Those three will become mutually orthogonal unit vectors. And we know what are the mutually orthogonal unit vectors on X. On X, it will be 1, 0, 0. Right now? Let me denote it by E1. On Y, it is 0, 1, 0. On Z, it is 0, 0, 1. Therefore, this will be a collection of unit vectors which are mutually orthogonal to one another. Then this set is defined to be orthonormal set. Correct? Let me write the definition. Okay? A non-empty orthonormal set. Orthonormal subset, a non-empty subset, say E1, E2 up to En, or one can write as simply Ei, depending upon the dimension of the corresponding spaces. Ei of a Hilbert space H is said to be an orthonormal set. Is said to be an orthonormal set if, what are the conditions? The first condition is Ei is orthogonal to Ej for I not equal to j. Why we are saying I not equals to j? Because E1 cannot be perpendicular to E1. If it is so, E1 is 0. Right now, 0 is the only vector which is perpendicular to itself. Therefore, here we want this set to be the set of unit vectors. Therefore, Ei orthogonal to Ej for I not equals to j, or one can write inner product ei with ej is equal to 0 for I not equal to j. The first condition simply means that a vector ei is orthogonal to all the remaining vectors except itself, right? Condition number 2 tells us that norm of ei is equal to 1 for all I. Norm of ei is equal to 1 for all I, or one can write inner product ei with ei is equal to 1 for all I, because norm ei is equal to 1 will give you us norm square ei is equals to 1, which gives us inner product ei is equal to 1, right? Therefore these are the two conditions. Okay, first condition means that a vector ei is orthogonal to all the remaining vectors. Second condition, ei itself is a unit vectors. Okay, therefore here one can say that the orthonormal set is collection of mutually orthogonal unit vectors. Mutually orthogonal unit vectors. Here example I have told you in the R3 space. In the R3 space, XYZ axis are the mutually orthogonal axis. On those axes, we will consider the unit vectors. We know the standard basis is the unit vectors, correct? Therefore, E1, which is 1, 0, 0 along x-axis, E2 is 0, 1, 0 along y-axis, E3 is 0, 0, 1 along z-axis. These are the unit vectors and also mutually orthogonal. Therefore, this forms the orthonormal set. Okay, now we will write some small note on the definition. The first note is an orthonormal set cannot contain a zero vector. Quite but obvious, right now? An orthonormal set cannot contain zero vector. Why it cannot contain a zero vector? Because norm of a zero vector is 0, which spoils your second condition. Number 2, if the Hilbert space contains the zero vector, only zero vector, then it do not have any orthonormal. If H contains only zero vector, that is H is equal to singleton 0. H is equal to singleton 0, then it has no orthonormal set. It has no orthonormal set. Third, if a Hilbert space is non-zero, then it possesses the orthonormal set. Every Hilbert space H not equal to singleton 0 possesses an orthonormal set. Possesses orthonormal set. Correct now? See, these may be the important points, important tricks for your multiple choice. If your exam be online, then these tricks is going to help you. Okay. Now, what this third note means actually, if a Hilbert space is non-zero, then it possesses the orthonormal set. How it is going to possess an orthonormal set? In this Hilbert space, we will find the collection of mutually orthogonal vectors, surely non-zero. Then we will try to convert those vectors to unit vector. How one can convert this? How can we convert a non-zero vector to a unit vector? Yes, anybody from the students can answer this question? How a non-zero vector is converted to a unit vector? Yes. Anyone from students? Non-zero vector. By which scalar you have to divide?
Multiplicative inverse.
No. You have to divide by its modulus, na? Its norm. Correct, na?
Yes, yes.
If we have a vector, say x not equal to 0, I'll write here. If suppose we have a vector x not equal to 0 here, which is not a unit vector, then in order to convert this vector to a unit vector, what I have to do? If I will take, if I will find its norm and divide the vector by its norm value, then what will be the, actually in the metric spaces we are dividing by modulus, na? X upon mod of x we are writing, but here in the norm spaces we are finding the distance by norm of x. Therefore instead of modulus we will divide it by norm value. Let me call it as, say, e. Okay, then what is the norm e value? Check. This is norm of x upon norm of x. Norm x is a scalar value. Let us take it out with the modulus. But as it is already a non-negative value, no need to write a modulus. Therefore, this is 1 upon norm of x into norm of x, which is 1. Therefore, every non-zero vector, if it is divided by its norm value, that is its length, na? Then the value is going to be 1. I can show this in the R2 space. Suppose this is my vector. This is my vector. I'll call 1, 2. In R2, we are discussing. Let me call this as x. What is the modulus value or norm value? Time being, let us take this by a distance formula. What is the value? Modulus value, this is 1 square plus 2 square. Therefore, 2 square, 1 and plus 4, this is root 5. Right now? Therefore, if this vector is being divided, if this vector is divided by its norm, what will be the vector? Vector will be 1 upon root 5 and 2 upon root 5. Correct, na? Now let us find its norm. I'll call it as E. What is norm E now? What is norm E? Under root 1 upon root 5 bracket square plus 2 upon root 5 bracket square. What is the value? One can tell me. This is
1.
1 by 5 plus 4 by 5, right now? Which is 5 by 5 and hence 1. Okay? Have you got it?
Yes, ma'am.
Okay, therefore, where is the location of your vector? Dividing by root 5 means we are dragging the vector x back. Here is your location x. Now we are dragging the vector x back by the scalar root 5, and somewhere here is the position E. And this position will be 1 upon root 5, 2 upon root 5, where this distance is unity. Correct, na? This is the method. Therefore, if we have a collection of mutually orthogonal vectors, though they are not unit, we can make them unit vector by dividing by their norm. Okay. Therefore, I'll write this as a fourth note. If set x1, x2 up to xn is the set of mutually orthogonal unit vector, sorry, mutually orthogonal non-zero vectors. We don't know whether they are unit or not. Mutually orthogonal non-zero vectors in H. Okay, in the bracket I will write not necessarily unit vectors. Those are not the unit vector, not necessarily unit vectors. Now, whether this set will be an orthonormal set? Surely not, because though they are mutually orthogonal, but they are not unit vectors. Then what should we do? We will convert every non-zero vector in that set to a unit vector. And how can we do this? How can we do this? We are going to call it as set EI. We are going to do this by dividing the vector with its norm. Correct, na? Therefore, the set will be x1 upon norm of x1, x2 upon norm of x2, and so on. This is xn upon norm of xn. Okay, and dividing by their norms does not affect the mutual orthogonality. Correct, na? How? Let us check. In R2, I will show only. Okay, Suppose these are the two vectors orthogonal to one another, na? Say x1 and x2. These are orthogonal. Now these are not unit. Therefore, what we have done, we will divide the vector by their norm. And somewhere is this the location, say even. Correct now? What is even? X1 upon norm of x1. As I have shown you in this example. We are dragging this x back to E. Right? Here also we are dragging x1 back to E1 so that E1 will be a unit vector. Same location, same procedure we will do for x2. Here we are dragging x2 back to E2 so that it will be a unit vector. Now just check whether there is a effect on the orthogonality of E1 and E2. No, surely not. Therefore, E1 E2 are still orthogonal to one another. Therefore, here also dividing by their norms, every vector we are dividing by their norm does not affect the orthogonality of those vectors, and hence this becomes the orthonormal set. This becomes the orthonormal set. Correct now? Okay. Therefore, example I can write is of example I can write as L2n. L2 is in a Hilbert space we have seen. Okay. And I will collect all unit vectors. Standard basis. What this E1 to N is? Standard basis. If it is a standard basis, may I say surely those are the unit vectors and those are mutually orthogonal to one another. Under the inner product, you can check under the inner product xy summation xi yi bar. Okay, hence this is the example of orthonormal set. Orthonormal set. Okay, now come to the important theorem. The theorem number is now 15, I think, right? Now this is 15. Now the theorem we are going to prove that an orthonormal set is always linearly independent. Okay, therefore let me write the statement. An orthonormal set, an orthonormal set in an inner product space X is linearly independent. Is linearly independent. See, whenever we are writing this as an inner product space, we cannot give the guarantee whether it is finite dimensional or infinite dimensional. If it is finite dimensional, it is easy for us to show that the set is linearly independent. But what to do for the infinite set? Okay, if the set is infinite, what to do? Then in this case, we will show that every finite subset is linearly independent. Okay, are you getting me? If orthonormal set under the consideration is an infinite set, then to prove it as linearly independent, we will prove that its every finite subset is linearly independent with this statement. An infinite set is said to be linearly independent if its every finite subset is linearly independent. Now we will make use of this statement to prove our result. Therefore, assuming a general case that it is infinite set. Okay. Therefore, here I'll write let S be an orthonormal set set in a Hilbert space H. Now to show that S is linearly independent, we have to show that every finite subset of S is linearly independent. Means here we are writing the proof by assuming S is infinite. But if S itself is finite, no need to worry. You can continue the proof directly. Okay. Therefore, this is the more general. Therefore, here I'll consider let S1, I'll write some finite value, some E1, E2 up to En be a finite subset, a finite subset of yes. Okay, now what to show? To show that this is linearly independent, what the procedure is, we will consider the linear combination of these vectors is equal to 0, and our aim is to show that all the scalars involved in the linear combination is equal to 0. Therefore, let me consider summation I from 1 to n alpha I ei is equal to 0. Okay, which actually means alpha 1 e1, alpha 2 e2, so on up to alpha n en is equal to 0. Let me call it as statement number 1. Now to show that these scalars alphas are zeros, alpha i's are the scalars. Now to show that the scalars are 0, we will consider the inner product of this linear combination with any arbitrary vector of the set S1. Therefore, I will consider now inner product summation I equals to 1 to n alpha I ei with an arbitrary vector ej. Okay. Now, this first coordinate is the linear combination. First, we will consider it as an addition. Okay. Therefore, using linearity property of the first variable, how can I write this? I can take those scalars out and I can write this as a summation of all the inner products. Therefore, may I say it is summation taking scalars out. This is inner product ei with ej. Hmm? Any doubt with this statement? Or shall I show you how it works actually? I'll just take a different color pen. Okay, here it is summation alpha 1 E1 added with alpha 2 E2, so on up to alpha n En inner product with Ej. Using linearity, how can we write? Alpha 1 is taken out, inner product of E1 with Ej added with alpha 2 is taken out, inner product of E2 with Ej, and continue this alpha n is taken out, inner product of En with Ej. Now look at this right hand side. This is a summation alpha I inner product ei with ej. Correct now? We have written directly. Now just continuing this previous step here. Continuing the previous step. What is the inner product ei with ej? Inner product ei with ej. According to the property, we know ei's are orthogonal to ej's for I not equal to j. Therefore, here we know the value of ei ej will be. I'll write here. Inner product ei with ej is equal to 0 for I not equal to j. And what for equal to j? 1 for I equal to j. For I equals to j. Now what we will do? We will run the sum over I. Okay. First term is I equal to 1. 0. Second is I equal to 2, 0. Somewhere in between we will get I equal to j. That will be 1 and all the rest are 0. Therefore, may I say this sum, if I continue here, this will be alpha j inner product ej with ej. All the rest terms are 0. But what is inner product ej with ej? This is 1. Okay. Therefore, what we have obtained? We have obtained this as equal to 0. Now let us check on the left hand side. Left hand side, this inner product we have considered 0. Therefore 0 inner product is a. Okay. Now what is the value? Sorry, here it is not 0. This is alpha j. Na? Inner product 0 with ej is 0. Right now? In an inner product, if any one of the variable is 0, the inner product gives you the value 0. Therefore, here we have obtained alpha j is equal to 0 for all j. Alpha j is equal to 0 for all j. Therefore, whatever is the scalars we have used in this linear combination, all the scalars are 0. Therefore, from 1, may I write S1 is linearly independent. What S1 is? S1 is finite subset of yes, and every finite subset is linearly independent. Thus, S is linearly independent. That is orthonormal set. An orthonormal set is linearly independent. Hence the proof. Any doubt for this theorem from student side? If you have a doubt, you can ask. Okay. In the next lecture, we are going to deal with the, let me just share my screen. Okay. In the next lecture, we will go to see what is the Bessel's inequality for finite orthonormal set and infinite orthonormal set also. Okay. In today's lecture, we have covered two theorems along with the definition of a orthonormal set. If you have a difficulty in this, you can ask, please. Yes, from student side, any difficulty? If not, thank you for watching today's lecture.